welcome David by, who you probably know from his fantastic notes that I personally used. Yeah, thanks, David. This is actually great. I didn't think I would meet you one day, and then you just come to give a talk. So today's talk is about 27 lines on a smooth cubic, and I think I will let David start.
Thank you for the introduction. So I'm going to first talk about algebraic geometry in general, as to why and how we're doing algebraic geometry. So I'm going to start with some motivation. So back in school, back when we were all young and naive, we learned this thing called coordinate geometry. We realized that sometimes when you face a very hard problem of Euclidean geometry, we can very often simplify it by replacing the circles and lines with equations. So for example, a line would have equation ax plus by equals c, and a circle would have equation x minus x naught squared plus 1 minus y naught squared equals r squared. Now we all know about this. And this turns out to be a fantastic way to solve many geometrical problems we have. But of course, now we went into university and we thought, how can we generalize these things? How can we generalize this kind of geometry, this kind of algebra, in a more advanced setting? The most obvious way to generalize this is actually differential geometry, where you replace lines and circles with differentiable manifolds. So things that you can locally parameterize. So lines and circles become, I'll just write manifolds. And this just gives you a whole lot more object to work with. For example, maybe we can work with the solution of heat equation. You can work with some random stuff that you make up, and it's very easy to be differentiable, it turns out. So you can talk about a lot more objects, but at the same time, when you have too many objects to talk about, you kind of lose that kind of rigidity, because in differential geometry, what very often happens is that we have a curve and you perturb it a little bit, it's still a curve. But that's not good if you want to find results that are combinatorial. In the case of lines and circles, I can say the following theorem. A line and a circle on the plane intersect at most 2 points. That's a theorem I know from the algebra of the situation. But I can't do this with just any differentiable curve, because this can go completely wild. So another direction of generalizing this is algebraic geometry, where you replace lines and circles with solutions to polynomial equations. And turns out this gives you a lot of rigidity and a lot of combinatorial result to work with. So by solutions to polynomial equations, I just mean, for example, if you're in R2, maybe you are looking at the solution of y minus x squared equals to 0, and this is a polynomial in 2 variables, and this will look like something, well, we all know what it looks like, something like this. And maybe you want to go a little bit more advanced, maybe you want to care about y squared minus x cubed plus x equals to 0, and this gives you something called elliptic curves. It's actually quite hard to control, but it's something like this. And although there are more varied than lines and circles, we can still talk about, for example, intersections. For example, if I say I want to see what's the intersection between this graph and the line, I can say, well, there are most 3 of them, because if I have a line that might be of the form y equals to mx plus c, and I plug this in, and this only has 3 roots, so there are only 3 choices of x coordinates, and you do something else. this gives only 3 points. So these are things that we're interested in. But it becomes quite obvious that vector spaces isn't the best place to do this. So this all happens in R2, which is a vector space. Sometimes you care about geometry in C2. There isn't any more particular reason to do so, except the fact that C is algebraically closed. So I can say stuff like a circular line always intersects at 2 points, counting multiplicity. But no matter R2 or C2, or in general Kn, where K is a field and N is some natural number, there is always something that's lacking. You realize pretty quickly that this space is somehow incomplete. What I mean by that, so in the case of, let's just say in the case of R2, morally, you want a theorem that looks like 2 distinct lines must intersect, which is false because you have parallel lines. But morally, parallel lines should intersect. They should intersect at some point at infinity. And it's also clear that you can't just have 1 point at infinity, because so this family of parallel lines should intersect at the same point at infinity. But that family of parallel lines should intersect at somewhere else. So we kind of want to incorporate this kind of infinity point in our calculations, because, well, the main reason is because they allow us to produce better theorems. But also, you kind of can't really do anything clean when you're doing things in vector spaces, or sometimes called affine spaces. So in this case, you know that, well, I only have to add 1 infinity point for each family of parallel lines. How many families are there? We have our origin R2, and for each slope, I need to add 1 infinity point. A slope can take value either in the real numbers, or it can be infinity when the line is vertical. So as a set, I want to consider this guy. But this guy is horrible. You can't do any more than line geometry with it. This is just a random collection of points. Even if you replace R by C, this is just the same. So algebra isn't going to solve the problem here. So we kind of want a systematic way to talk about this kind of thing, while also incorporating the kind of polynomial geometry. We want to make sense of polynomials in this situation. So formally, this is a construction called projective spaces. The formal construction of this is, some people find it a little bit weird, some don't. I certainly feel like I certainly want this audience to find this natural, because we're going to use it a lot. So I want to construct a projective space Pn while fixing a field over a field K. In most cases, as I said, I will take K to be the complex numbers, because that's just what most situations will take place. But in this discussion and everything else in the top, you can replace C by any algebraically closed field whose characteristic is not 2. And I actually start with K, the vector space Kn plus 1. So that's the collection of n plus 1 tuples, x0, x1, etc., until xn, where every entry is in my field K. And as I said, I can as Pn to be Kn plus 1, removing the 0 tuple. And I want to take the quotient with respect to an equivalence relation. And the equivalence relation says x0 until xn is equivalent to lambda x0 until lambda xn. well, lambda is in K, but it's non-zero. So this is a fine definition of sets, but certainly we want some coordinate on it, and the coordinate on Pn. So every point on Pn is essentially an equivalence class of this equivalence relation, and we represent it by giving a representative of this. So this is often written as x0 colon x1 colon. I use a colon here because this is essentially a ratio of all the entries. Okay, so this is how we'll identify a point in Pn. Now, from the start, it doesn't seem quite obvious that this does extend the vector space Kn. Certainly, we want to include Kn inside it, and whatever is not in Kn should be our points at infinity. And they should be relatively. There shouldn't be many points at infinity. It shouldn't come. Yeah, there shouldn't be many. So let's see how this works. We first consider set x0 is non-zero. Now this is a perfectly well-defined set in Pn, because if x0 is non-zero and you multiply it by a non-zero scalar, it's still non-zero. Likewise, x0 equals to 0. It's a perfectly good well-defined set in Pn. Now, how are the coordinates in this set works? A point in this can be represented by x0, x1 until xn, where x0 is non-zero. But since x0 is non-zero, I can multiply by some scalar to make x0 1. I'll write y1 until yn. So every point in this set has a unique representation, where the first entry is 0. But these are just the coordinates on Kn, right? So x0 not equal to 0 can be identified with Kn. So x0 equal to 0 is naturally what we have for the infinity points. And it does make sense, because let's just take n equals to 2. Then everything 1, y1, column 1, y1, y2 gives you the points in the plane. And if y1 is non-zero, then I can also multiply by one inverse, and 0, 1, m. These are the slopes where things are not vertical, and 0, 0, 1 is that's one slope where everything is horizontal. So it does give you what our intuition is for the projective plane. Now, since we have the coordinates for the projective space, we can also make sense of polynomials in those variables. But not all the polynomials can work. For example, if I consider polynomial x0 plus 1, and then I ask, why is x0 plus 1 equals to 0? It's kind of it just doesn't work, because say I have a point 1, 0, 1, 0, 0. You'll say, well, this point does not solve this equation, because 1 plus 1 is 2, which is not 0. But there is another representation of the same point, which says -1, 0, 0. They're the same point, but this does solve this equation. So it can't just make sense of any polynomials. But instead, we can make sense of homogeneous polynomials. So these are the polynomials, all of whose monomials are, all of those monomials have the same degree. So this has things like x0 squared plus x1, x2. So this has degree 2 and this has degree 2, so it's homogeneous. Maybe x1, x2, x3 plus x1, x0 squared. Yeah. So these are all homogeneous. And we can make sense of when does this vanish. We can't quite make sense of the value, but we can make sense of when do they vanish. Because if there's one representation where this expression vanishes, then for any other representation, when I multiply each of x0, x1, x2, x3 by lambda, this whole expression is just going to be multiplied by lambda cube. But lambda is invertible, so we can just delete it from both sides. So homogeneous polynomial, so zeros of homogeneous polynomials now make sense. And you can also check that if you want to consider a just normal polynomial on the normal coordinates on Kn, then you can always extend it to be a homogeneous polynomial on Pn, because you have one more variable. So you can always set that variable to be 1, and then you get a perfectly normal polynomial. So in this case, our setting for algebraic geometry would be to consider things like, consider the solution of the simultaneous polynomial equations, f1 equals 0 until fr equals 0, where f1 until fr are homogeneous polynomials in x0 until xn. And we already know that this makes sense. And this gives us a lot of algebraic objects to work with. So these are the settings for algebraic geometry. Let's check. Yeah. I will just add a final remark. Actually, 2 final remarks. Firstly, Pn is very, 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 very symmetrical. What I mean by that is that we can change coordinates. So this kind of reflects to what we are doing with coordinate geometry, because if my geometrical problem contains a very, very important intersection, you would want to put that intersection in the origin, at the origin, because that simplifies all your calculations. And this would be a trick that we will use to simplify our calculation. If you know a little bit about group actions, what I mean by this precisely is that GL n plus 1k acts on Pn by multiplying the matrix to the vector that's given by the homogeneous coordinates. And this action is kind of the best you can hope for. It brings any points to any points. It brings any lines to any lines. It brings any planes to any planes. With a little bit of analysis, you can also show that it brings 3 disjoint lines to any 3 disjoint lines, and that's what you can do. But we'll not care much about that. But the point is, if I have a line, I can feel free to put it to I can feel free to put it wherever I want, and usually I put it as well, maybe vanishing of some coordinates because they are the easiest to deal with. The second remark is about P3, mainly because we will be interested in P3 and P2, which is the following. I don't want to call it theorem, but it's just the following statement. In P3, any line intersects any plane. So a line is basically the intersection of 2 planes, and a plane is a vanishing locus of a linear homogeneous polynomial, a linear form. So you're basically solving. So a line says that you have 2 linear forms in 4 variables, and a plane says that you have 1 more linear forms in 2 variables in 4 variables. And these are 3 equations in 4 variables, so certainly they have a non-zero solution, and that's why they have an intersection. You can very easily formalize this, but I don't have time to do that because we want to talk about this theorem, which is my section 3. This theorem is basically the first, I think I think the first non-trivial result in this geometry of, well, it's called enumerative geometry. So it says the following, and I will explain some of the terms afterwards. So this is due to Cayley and Salmon in 1847 or 1849. 1849. So any smooth cubic surface in P3 contains exactly 27 lines. And by cubic surface, I mean the solution of f of, so P3 has, the coordinate on P3 has 4 variables. I'll call them x, y, z, and w. The solution of this equation where f has degree 3. F is homogeneous of degree 3. So an example of this would be maybe x cubed plus y cubed plus z cubed plus w cubed equals 0. So this will be my f. And if you have time, you can try. It's not actually very hard to find all the lines on this surface. And yeah, there are exactly 37 of them as predicted by the theorem. I should also say that here I'm taking my k to be the complex number. Did I say that already? But anyways, this is algebraically closed, so I don't have to worry about things like, oh, maybe this doesn't even have any points at all. It has to have a point because of fundamental theorem algebra. So, and there is another notion that I have to care about, which is a little bit more complicated to explain in general, which is smooth. The definition of this, if you actually do algebraic geometry, and you take the corresponding course in part 2 and part 3, you'll come across at least 4 different definitions of it. And you'll work very hard to show that they are indeed equivalent. But in this case, if I only care about cubic surfaces, I can say this just means that the partial derivatives, I'll write gradient. The partial derivatives don't all vanish on any points, on any point on, let's call this S, at any point on S. So just to give an example of a surface that's not smooth, if I take S, just f equals to x squared y, then this won't be smooth because this is 0 at 0, 0, 0, 1. So, so that's a theorem. That's the correct statement of this quite famous results to Cayley and Salmon. And of course, we're going to prove this. We have half an hour left, which is definitely enough to prove this. The first thing I'm going to say in the proof is a little bit, I want to say blasphemous, because I want to assume something that's completely non-trivial. And I will explain how to prove this at the end, because that turns out to be the most important part of this theorem. Assume that S does contain a line. One line. It turns out, if you assume it contains one line, it's not actually very hard to show that it contains contains exactly 27 lines. Okay, I'll make this assumption here. So our strategy is as follows. It's hard to find lines on a surface because we know very few about surfaces. But it's easy to find lines on planes, right? So what we're going to do is we're going to try to consider a set of form S intersect H, where H is a plane. So H is a vanishing of some linear form. Linear form equals 0. But of course, we can't just take any planes. But let's just see what possibilities can occur. Now, I shouldn't have to explain that if I intersect a cubic surface with a plane, I get a cubic curve, right? And what options do I have? If I have a cubic curve, if I have a curve defined by a cubic equation on a plane, it can either be irreducible. The polynomial can either be irreducible, in which case you get something like this. Don't worry too much about this one. Or it can factor as a irreducible quadratic and something linear, in which case you get a conic and a line. Or it can factor completely. It can factor into 3 lines. In this case, there are actually more than one situation that can occur. I can have 3 distinct lines, or 2 of the lines can be the same. This happens if your curve is something like just x squared y. Then, yeah, then essentially this linear form is counted twice. Or all 3 lines can be the same. Maybe you have something like 3x cubed. Now this is where smoothness comes in. You can check, and it's not very hard, but I don't think I will do it here. But you can check that if this or this occur in this intersection, whatever the plane is, if this or this occur, then S cannot be smooth. If you want to simplify your calculation on that one, you can just assume H is the vanishing of W, because you can always change your coordinates until H is actually just a vanishing of W, and it does not change the definition of smoothness. So this and this cannot occur. We should use, yeah, I'll just cross that way. Now, we assume that S contains 1 line, so it doesn't quite make sense if we just throw a random plane and cut it through it and see what happens. So let's just say if H contains this line L. If H contains L, what happens? It can't be this case either. It can't be an irreducible cubic because it does not contain the line. So we are left with this 2. Now, both of them can occur, but it's clear which one we want. If it's a conic and a linear, if it's a conic and a line, it's completely useless because we want more lines. If it's 3 lines, I guess 2 more lines. So we want to know exactly when does this happen, which involves some algebra because we've just been doing geometry so far. So certainly we'll need some algebra to cut there. So as I said, you can change your coordinate. So I can just choose my line to be the best line possible. So my line L, I will assume with a lot of generality that it's defined by the equation z to w equals to 0. So if this were true, then H would have to have form lambda z minus mu w equals to 0, where lambda and mu are in my field K. They are allowed to be 0, but they just don't put not both 0. All right. And we want to calculate the intersection. The first thing we're going to do is to calculate what H actually is. So H, in terms of coordinates, is essentially xy. I should be using the column here. mu t lambda t, where x, y, t are in K. So a plane in projective space is just a projective plane. And x, y, t here is essentially the coordinate you have on this particular projective plane. Now, this does not quite give us a way of calculating immediately. So let's see how our change of coordinate here simplify our calculation. We can't do it with a general cubic because there are 19 cubic, there are 20 cubic monomials in 4 variables. So it will just be horrendous. But if it contains this line, what does it mean? It means that whenever one of Z and W vanish, my cubic form F should vanish. So F cannot contain linear forms like x cubed. So F cannot be x cubed because this will contain this line. It also cannot be like y cubed or x square y or xy squared. Everything must either contain Z or W. Now, if you think about it, if everything either contains Z or W, then the combined degree of x and y in every monomial cannot exceed 2. So essentially, I can write F in this form. I can write F as ax squared plus bxy plus cy squared plus dx ey f, where a, b, c, d, e, f are homogeneous polynomials in Z and W of appropriate degree. So for example, A would have degree 1, and F would have degree 3, and D would have degree 2. So we know that if F contains L, it must be of this form. And we know a lot about conics. We know a lot about quadratic forms. So in terms of the coordinate x, y, t on H, what would my cubic curve be? I can just substitute this in, can't I? And what I get is f of a, f equals to a x squared t. Now, here, I'm assuming a, b, c, d, e, f are now polynomials in lambda and mu, because I've substituted it in. So maybe I should write a of mu lambda, but that's a lot to write. So yeah, just one clear head. bxyt plus cy squared t plus d xt squared plus e yt squared plus ft cubed. Now I can take the t out. So it's t times, well, you know what goes here. And what goes here is like ax squared plus bxy plus cy squared, etc. And we know that if this is 0, then either t is 0, which gives you a line, and that line is my original line, or this part is 0. So it's 3 lines if and only if this part, which is a quadratic form, is irreducible. Because if it's reducible, then I get some linear forms times some linear form, which gives me 3 lines. If it's irreducible, then it just gives me that irreducible conic. So we've changed the problem to when is this quadratic form degenerate? And we know exactly when the quadratic form is degenerate. Well, I didn't want to write the equation down, but it looks like I will have to anyways. So this quadratic form is x squared plus bxy plus cy squared plus dxt plus byt plus ft squared. I'm hoping this was covered in vectors and matrices. It's certainly covered in linear algebra, but this guy is irreducible if and only if it has non-zero discriminant. Because you can write this as xyt times this matrix, which it should be something like a b over 2. There should be something like a b over 2, d over 2, b over 2, d over 2, e over 2, d over 2, c and f times xyt. And you know that this is irreducible. This is non-degenerate. If and only if this guy has non-zero determinant. What is the determinant? I don't really care about what the determinant exactly is, because whatever it is, it's going to be horrible for calculation, and I don't want to do a calculation. But I do know what the degree of it as a function of lambda and mu. Now, let's just take a typical term in determinant expansion. ACF. A has degree 1, C has degree 1, and F has degree 3. So this has degree 5. B over 2, E over 2, D over 2. B has degree 1. E and D have degree 2. So this is also degree 5. So it turns out every monomial that ever occurred in the expansion of this is a degree 5 monomial in lambda and mu. We're not quite done because it can be 0, but I will leave to you to check that if everything cancels out, then your original cubic form can't be irreducible, in which case there's if it can't be irreducible, then it's certainly not smooth. So there's that. So essentially, what we have is that if I consider all the planes mu z minus lambda w equals 0, I hope that's what I started with, but it's all the same anyways. Then the solutions. Then for this to produce a 3-line configuration after intersecting with S, mu and lambda must satisfy a polynomial equation of degree 5, which has almost 5 roots. So that's where the rigidity of algebraic geometry comes into play. Now, I'm going to ignore the next part of the proof, which is to say that it has exactly 5 roots. And there is nothing really important going on there. It's just calculations. So I will leave it for you to check. But this basically the smoothness of the cubic guarantees that, as you might have expected. So we've concluded the following. I'll write it as a I will have a conclusion of the claim because we have proven it. Conclusion: if L is contained in C, where L is a line, then there are exactly 5 planes through L. Five planes, let's say a typical plane is H, such that H intersect S equals to 3 lines. These 3 lines might as well intersect. I don't care, but it's 3 lines. In particular, S contains exactly 10 lines sharing a plane with L. So we're actually making progress. We're given 1 line, and we ended up with 11 lines. And to finish the proof, we'll just say, well, we just take any such h. So there's a plane h. The intersection with S is 3 lines. Now, for each of these lines, they share plane with 8 other lines. So there are at most 3, which are things on the plane, plus 3 times 8. And this is 27. We also need to make sure that we didn't double count. What if, when I'm counting lines that share a plane with this line, I double counted it, and I also counted the same line while I was checking lines that share plane with this. There is one line, the obvious share plane with either of those two, which is this line, but we've already discounted this line. So if any other double counting happens, it must also go through the intersection point between these two lines. Because if it's not, then it's just not gonna work. So you have 3 lines that does not share a plane, but they share a common intersection. Now, by change of coordinates, I can assume, so if you have 3 lines in just a vector space K3, just think about R3. If you have 3 lines, the most intuitive thing to do is to put them on the axis, right? So if I put them on x equals to y equals 0, y equals z equals 0, x equals to z equals 0, then this is essentially saying that every monomial in my f must contain, well, let's put it this way. Every monomial of my f, its degree in x, y, and z must be at least 2. But such a monomial such a qubit form must be not smooth. It cannot be smooth as a point 0, 0, 0, 1. So that cannot happen. So there are exactly 27 lines, and we are done. Except we haven't. Because at the beginning of my proof, I said my surface contains 1 line. And it's completely not obvious that my surface should contain 1 line. I mean, there is an elementary proof, but that involves a lot of calculation and does not actually offer any. Well, it has some insights, but not much. The proof I'm going to show you is not going to be elementary, but I think you understand the heuristics behind this. If I can spell heuristic correctly. Heuristic. Yeah. The heuristic is, there are 2 heuristics I'm going to use. The first one is the following. If I have something, if I have a blob whose dimension is m, and I have another blob whose dimension is m and n, and I have a map, so let's call it x, y, and then a map f between them, then, so I'm also gonna assume that for any y in y, the preimage of y has constant dimension r, let's just say. The first heuristic says that n minus n should be r. Let's say r is greater than 0, just so that it's guaranteed. It's just so that it's guaranteed that it's surjective. My first heuristic is that n minus n equals r. Now, you've seen stuff like this a lot. For example, if my x and y are vector spaces and f is a linear map, then this is true by rank nullity theorem. If x and y are differentiable manifolds and f is smooth, then this is also true. This is a combination of preimage theorem and Sod's theorem. And now I'm just saying that the same thing works if I'm doing algebraic geometry. The second heuristic is much more problematic. And by problematic, I mean, you might not have seen a situation where this is true. If m equals to n, which is, by the way, this is not actually the I mean, this somehow just work as a statement if you assume x and y are what's called projective varieties. But this is not actually the hypothesis. But anyways, if m equals to n and f is non-constant, we expect f to be surjective. Now, anyone can give me 2,000 counter examples to this side. But this is true when, for example, f is an open map and x and y are compact and Hausdorff and connected. And you've also seen stuff like this in Riemann surfaces because, yeah, compact Riemann surfaces are connected and compact Hausdorff. So these are the two heuristics I'm gonna use. Let's see how this gives me. Let's see how this gives the result. So, and there is actually a third thing I'm gonna quote, which might not be obvious, but okay. As I said, I let G to be the set of lines in P3. It's absolutely enormous set, but the fact G has dimension 4. This is, I would say this is not counterintuitive. I hope it's not counterintuitive because a line is intersection of two planes. A plane has 4 coefficients. Well, it actually has 3 degrees of freedom because you can multiply everything by a non-zero scalar. So a plane, choosing a plane gives you 3 degrees of freedom. Choosing 2 planes give me 6 degrees of freedom, but I can always rotate those planes around my line, and it's not going to change my line. So I deduct 2 degrees of freedom, and I end up with 4. And I let y to be the cubic forms. Let's say cubic surfaces, because we've introduced that terminology. Cubic surfaces in P3. Now, I think I also said it before, but the number of cubic monomials in 4 variables, how many are there? Well, there are 3 plus 4 minus 1, choose 3, which is 20. But we don't actually have 20 degrees of freedom because, again, we can multiply everything by a non-zero scalar, and it's not going to change anything because we are just solving this cubic form is 0. So we deduct 1 and conclude that y has dimension 19. Now these two objects are not weird. They should be intuitive enough to think about. Now x is something weird. X is a subset. So the subset of G times Y, of the product set G times Y, such as G, which is a line, is contained in Y, which is the surface. Now we care about this thing because we want to know when this line is lying on surface. And we also know that X is non-empty. Just a little bit sanity check. Because there are cubic surfaces that contain lines. For example, maybe I shouldn't have chosen X, but anyways. For example, x cubed plus y cubed plus z cubed plus w cubed equals 0. This contains at least one line. So X is non-empty. Okay. Now, we don't know much about X because X is absolutely horrendous. Well, it's not horrendous, it's just complicated. But we know that X has some nice maps out of it. This is a map from X to G, which sends this GY to G. It's just the first projection map. So P inverse G is a set of cubic forms that does not vanish on the line of my choosing. Now, if my line is x equal to y equals to 0, then maybe I'll choose z equals to w equals to 0. Then what I'm excluding are, as I said before, what I'm excluding are x cubed, x squared y, xy squared, and y cubed. And there are 4 of them. So the dimension of this guy is going to be 19 minus 4, which is 15. And my first heuristic, dimension of x, would be dimension of g, which is 4, plus 15, which is 19. And we have another map, q, from x to y, which send gy to y. This map is even worse, but our second heuristic works now because y and x both have dimension 19. And q is not constant because whenever a cubic surface has lines, a whole bunch of cubic surfaces has lines by just rotating it around whatever line you choose. So this can't be constant. So this has to be surjective by our second heuristic. And if it's surjective, then what does it mean? It means that every cubic form have a pre-image, gy, but that just means that g is containing y. So that means that every cubic form, so it means that every cubic form has a line on it. So, of course, to actually finish the proof, I have to tell you why and when these heuristics actually works. And that is why we will need to develop algebraic geometry, because clearly this is the kind of method we can generalize. If you just go up, if you care about lines, maybe in this theorem about quintic threefold, maybe in even higher dimensions, we can't always do the trick of slicing a line through them and see what happens. It sometimes does work, but you would want something like this to help you conceptually know why and when is it true. And I'll just mention a last thing. So if you think about this dimension argument a little, you'll find that this is pretty precise. This all just rely on this 19, and this also has dimension 19. What if it doesn't? If it doesn't, then the number of surfaces that has lines would be absolutely tiny compared to all surfaces. So if you think about this argument a little, you'll find that if I care instead about a degree d surface, not necessarily d equals 3. When d equals 3 is just cubic surface. If d is greater than 3, then most degree d surfaces has no line. And for experts, by most, I mean a Zariski open, non-empty Zariski open set of the parametric space. But just, yeah, it's just something of a lower dimension. So the story doesn't actually end here. You can also ask the following question. If I let ND to be the maximum number of lines on a degree d surface, given it does contain finitely many lines, then what is ND? So Sanger showed in 1943 that ND is bounded by d minus 2 times 11 d minus 6. However he did it. But that bound is far from sharp. And we can also try by constructing surfaces, which is actually quite hard. And that gives you that does give you some lower bound, which is also quadratic. So we know asymptotically it's quadratic in D, but the general case is actually still open. So I guess the last thing I would say is just that, so sometimes it's good to have geometry objects that are not as floppy as in maybe topology and remaining geometry. And because that gives you such wonderful combinatorial results. And stuff like this, the heuristic like this is exactly the reason why we want to develop algebraic geometry in a higher context. And I'll stop here.
Thank you very much. Does anyone have questions?
Yeah, is it so? You did all of this on the assumption that every cubic can be embedded in P3?
Oh, this theorem is just about cubic surfaces in P3.
Oh, it's just about cubics in P3.
Yeah, yeah.
So, what about the more general case?
You'd have to define cubic surface in general cases, I say.
Oh, right.
Yeah. Maybe you can do it with devices, but that's because
right,
one
so
thing about lines and
depends on
surfaces
the
is that
embedding.
this is not invariant under polynomial math, on the morphisms.
Yeah.
Because a line, most of them don't take a line to a line.
Right.
So these 27 lines are definitely not functorial.
Okay. Yeah.
Yeah.
Sure.
And do you have like similar things for like conic sections?
I mean, for conic sections, first of all, conic section are curves. There are theorems about conic sections. There is this theorem, quite classic. I forgot who proved it, but I'm hoping I quoted this correctly. So if you give me 5 lines, I think it's 5. So given 5 lines on the plane, some writing board is getting wonky. On a plane, there are exactly 3,264 conics. That's a tangent. That's tangent to all of them.
Yeah. Okay. I remember seeing something about this. Yeah.
Yeah, and like weird number like this show up all the time because if you count the number of lines on quintic threefold, which is the solution of a quintic equation in P4, there are 2,874 lines, 75 lines. And certainly for those kind of problems, you can't just do it by hand like this. You also want like Euclidean formulas and whatever. But yeah,
Okay,
there are
yeah,
a lot of problems. There are a lot of problems. There are a lot of nice results, and there are a lot of open results as well.
So do we have anything about the inverse problem, where we have 27 lines and want to find a cubic surface whose lines are exactly those 27 ones?
So you can check it. One observation that you have to make is that if you have a quadratic surface, it contains a lot of lines, right? Conversely, if you have 2 lines, if you have 3 disjoint lines, you can uniquely find a quadratic surface that contains all of them. Because well, the easiest way is to because you can okay, by quadratic surface I mean a smooth quadratic surface, okay, and like you can diagonalize them, so they're actually all just the same. So okay, yeah. you can move it around. So 3 disjoint lines determines a quadratic surface, and you can just go from there.
Yeah. Okay. Yeah.
But I mean, certainly in general, if you have 27 lines, you're not going to find them.
What do you mean by disjoint lines, like non-intersecting?
Yeah, in P3 lines can not intersect because you can have like skew lines like this.
Okay.
Yeah.
So in terms of the set of lines on a cubic, is there any more structure on the 27 points or? Yes.
These 27 lines actually intersect as a fixed pattern.
Okay.
Yeah, and you can work it out. Actually, one of the proofs of the 27 lines result is to show first that the lines on cubic surfaces have the same intersecting pattern, and then say, well, there's this surface and its lines intersect like this, and you're done with that. But that's pretty hard. I mean, the most fancy proof of this is that apparently you can view a cubic surface as a blow up of the projective plane at 6 points.
Okay.
this is also the proof that's shown in Harshon. This is partly the most elementary proof that I know. I mean, you can do the last part. You can do the last part in an elementary way by using resultants, but you have to calculate some like 5x5 determinant and whatnot. So
is this from? So the proof that you showed is it treated in any book? You learned?
It is in the proof I showed, I think, is the original proof. And okay. I think I would recommend, I think many of you might have heard this book, right? Undergraduate algebraic geometry, where he also covered the case for, where he also covered the elementary proof that I mentioned. There's another book which references Reid's book, so I'm not going to put that there. Yeah.
Yeah, just for the anecdote, I think I remember seeing in Oxford, well, because I just was there for one day, an explanation that that Sylvester made the plaster models of cubic surfaces to draw the lines physically on them and show them during the lectures.
I mean, that's pretty hard. The hardest part is to find a cubic surface where all of the lines are actually real.
Yeah.
I think there are these surfaces like that's the image I put on already.
Yeah, actually, you think you can. Sorry, you just go on.
Actually, there is a corresponding theorem about real cubic surfaces. So I think it says that of those 27 lines, the number of real lines is either 3, 7, 15, or 27. No, it's might not. It's also a 19th century result, so it shouldn't be too hard. But
yeah,
the proof, I have not seen the proof, but I would guess it's something you just try to keep track of the Galois action along the way. Yeah.
Yeah, this is really fun.
Thank you.
But I really don't want to do the calculations myself. I'm really wondering how the people in
the point of algebraic geometry is you try not to do calculations because everything looks like they can be done with brute force calculations, but it's not really true. Yeah.
Okay, yeah. Well, if no one has questions, just leaving you 40 seconds if ever you have any. I will end the talk and thank you everyone for coming. And hopefully we'll have another talk sometime next week.